So in this video, we would try to find out what rubber is, right? Rubber is also a polymer, and we have rubber available to us in three different forms. You can have natural rubber, which is obtained from the extract of a rubber tree. Then you have the vulcanized rubber. This is prepared from natural rubber by some chemical processing, so we may even call this as semi-synthetic polymer or semi-synthetic rubber. And then we have completely synthetic form of rubber. These three forms, we would take up each form one by one. So the first one here is natural rubber. Now natural rubber is ideally an elastomer, and so basically it is elastic in nature, and it is manufactured from latex. Latex is basically a colloidal suspension which is obtained from the bark of a rubber tree, and a natural rubber is manufactured from it. Now let us understand the chemical composition of this rubber. So if you want to understand the chemical nature of natural rubber, it is basically a linear polymer of isoprene. Isoprene is the monomer unit, and it is also called cis-1,4 polyisoprene. Now let me show you the reaction by which, the polymerization reaction by which it is formed. All you need to do is like take isoprene. Isoprene is basically a structure like this. It is like a butadiene, 1,3-butadiene, and on the second carbon you have a methyl group, so 2-methyl 1,3-butadiene. If you take N molecules, this is isoprene, and then it undergoes polymerization. So when it undergoes polymerization, it would give us polyisoprene. It goes like this, CH2, and then you have, this shifts furthermore. So you get connection here, then this goes in the center, and this goes with the next monomer. So it's like this. Okay, what I can have is like C and then CH3, double bond, then C and then CH2, and then you have H, and then we have this CH2, and then we have C double bond, then we have CH3, and then we have CH2, C, and then H. This is then N times. Now why is it called cis? I would show you why it is called cis. You can see that this CH2, where it gets connected, and this CH2 are on the same side. Then for the next monomer in the chain, so both the CH2s which connect the monomers, they remain on the same side. So each molecule will have two CH2 remaining on same side. So it is a kind of cis polyisoprene. So I can now call this as cis polyisoprene. It is 1,4 polyisoprene, but the general name would be cis polyisoprene, right? You can even make synthetic, this is like polymerization of isoprene, right? There is this very special way of making it. There is synthetic rubber, which is obtained by free radical polymerization, which is obtained by free radical polymerization of isoprene, has trans configuration. you have to know that the synthetic rubber, which is obtained by free radical polymerization of isoprene, can have trans configuration. So when it has trans configuration, we call it as a very special name, gutta percha. This is, this is something which doesn't show as much elasticity as the cis isomer. So gutta percha has trans configuration in the same way, and it is not as elastic as the cis isomer. So let us take up some properties. The first one, it has a random coiled structure. So the polymeric chains are in form of random coils, and there are very weak van der Waals forces between the polymeric chains. So what happens because of this? When you apply force, these chains, they can be stretched, they elongate, they show elasticity, right? So when you apply force, the chains would stretch, and when the force is removed, the same coiled structure is formed again. Now, why would the same coiled structure get formed again? That's because of the presence of some crosslinks between the chains. So these polymeric chains may have some crosslinks, because of which the polymeric chains, they get retrenched back to the same structure, same coiled structure. Natural rubber maintains elasticity ideally between 283 to 335 kelvins of temperature, but then you may find that beyond that, natural rubber, lower temperature lower than 283 or temperature higher than 335, the elasticity of the natural rubber is to a large extent lost. Again, there are some other problems. Natural rubber has very high water absorption, so absorbs water, and because of which it gets spoiled. It is oxidized by oxidizing agents, so that's also a big problem. And you also find that it is soluble in organic solvents. So soluble in organic solvents. So that's also one of the problems. So all these are different problems associated with natural rubber, and because of which its application is reduced to a large extent. However, before we do that, there are still some uses that can be allotted to this. So let me put up some uses. Making things like hand gloves, disposable hand gloves. They are prepared from natural rubber. Normal rubber bands, they are again prepared from natural rubber, and even erasers are prepared from natural rubber. So all this together, right? And that's also one of the things that happens here, right? So we have it like this. This is all about natural rubber. As you can see that it is the cis isomer, but you can see that natural rubber has a lot of limitations. To overcome this limitation, right, there is one process which is done on natural rubber, which is called vulcanization. So let us understand what we have in vulcanized rubber. That comes next. So let us now take up the vulcanized rubber. Vulcanization of rubber was done ideally to improve the properties of natural rubber. Natural rubber has some of the very big problems associated with it. For example, it absorbs water, right? Again, it is easily soluble in organic solvents, right? Because it is organic solvents dissolve non-polar polymers, and this is absolutely non-polar in nature. So, and once again, it is also it does not sustain elasticity above 335 kelvins or below 283 kelvins of temperature. So vulcanized rubber, right, is a better version of that natural rubber. So how is vulcanization done then, right? Let us understand what do we have to do with natural rubber. A simple way to understand how a vulcanized rubber gets formed is like you take natural rubber and you add sulfur powder to it, and then you have to heat this mixture at a temperature of about 373 to about 415 kelvins in presence of zinc oxide as a catalyst. Once this is done, you get vulcanized rubber. Now, what happens in vulcanization? So let us understand that vulcanized rubber is formed by, it has sulfur crosslinks. Formed between polymeric chains of natural rubber. So we have sulfur crosslinks which are formed between the polymeric chains of natural rubber. So that is a very important thing that you have to know, right? Right, so this is very important. Now I shall give you the structure of how this happens, right? So if you want to understand how vulcanization takes place, look at this. This is the linear chain. This is where there was a double bond here, but double bond is now broken and you have the sulfur linkages formed, right? So the reaction of sulfur will either occur at the carbon-carbon double bond, or it may occur at the carbon which is just next to the carbon-carbon double bond. This is called the allylic carbon, and allylic carbon is also a very reactive form of carbon. So between two allylic carbons, right, of two different polymeric chains in natural rubber, there can be a sulfur cross link formed, or the double bond between carbon and carbon is lost and addition of sulfur takes place, and this is how the two chains get linked with each other. So this is the sulfur cross links at double bonds, and this is the sulfur cross linking at the allylic position, right? So this is very important, right? Now, what would happen because of such sulfur crosslinks? So you have to understand that when sulfur crosslinks get formed, first of all, the chains become more polar. So its solubility in organic solvents decrease appreciably, right? Because the chains become more polar, you've added a polar sulfur into it. Second, because of sulfur crosslinks, absorption of water cannot go between the polymeric chains because there are sulfur cross-linking, right? So absorption of water decreases, right? And cross-linking imparts hardness and hence rubber will not lose elasticity at lower or higher temperatures, right? So this would not happen. Again, the double bonds are lost because any oxidizing agent would attack the double bonds. Most of these double bonds are removed in cross-linking, so more stable towards oxidizing agents. So these are some of the properties which are acquired by natural rubber when you perform vulcanization. So it's a huge improvement in the properties, right? Now you have to know that when vulcanized rubber with 5% sulfur is used for making tires. And vulcanized rubber with 30% sulfur is used for making battery cases, right? So we do have different types of rubber formed with different amount of sulfur added, right? We can also have rubber. This is a third category, rubber added with 25% sulfur. Also has a special use, but it is called ebonite. It is called ebonite. So these are some of the practical uses. You may have many more uses, right? So these are not the only uses that you have, but these are some of the important uses that you have, right? Not the only uses, okay? So this is about your vulcanized rubber. How is it formed, the structure, and the improvement in the properties, and then we have the uses. The next we do is we move on to synthetic rubber. So let us start with the third category, synthetic rubber. Synthetic rubber is completely man-made, and you have three different types here: Neoprene, Buna-S, and Buna-N. Buna-S and Buna-N, we've already discussed the preparative methods in the previous videos, so we don't consider them now. We would talk only about Neoprene. Neoprene basically is obtained by polymerization of chloroprene, and you have to know what chloroprene exactly is. So we can have CH2. It is a kind of butadiene only, but on the second carbon you have a chlorine. So this is like N molecules, and you have, this is called chloroprene. And this chloroprene is then polymerized. So here we write polymerization. And this polymerization would produce, and once again the same, if you want to know the arrows, so it goes like this: CH2, CCl, double bond CH, CH2, N times, and this is what we call as neoprene. Neoprene has chlorine in it. The only difference between neoprene and our natural rubber is, like in natural rubber you have a CH3 here. With chlorine here in neoprene, there are a few things that happen. The properties change to a small extent. Now, first of all, any halogen like chlorine, when imparted here, would allow the polymer to show a good amount of just a good amount of just a moment. Okay, let me put it here. Yeah, it would show a good amount of heat resistance, because when you have chlorine, right, there's a lot of heat resistance. Again, polarity of the structure would increase, and because of which the resistance towards organic solvents like mineral oil or vegetable oil would also increase. So if we talk about the properties, I may directly put here properties. We may say superior resistance towards mineral and vegetable oils. That's one thing, right? And it is a homopolymer, right? Its heat resistance also increases. So for uses, we can have a few things like making conveyor belts, making caskets and hoses. These are all basic uses that we have with neoprene. And so there's this very little thing that you have to do about neoprene. There's one important thing which is an extra thing that you have to do of how chloroprene is prepared. Many a times you'll have to know this. So here I'm just giving you the synthetic procedure for making of chloroprene. So synthesis. This is not there in the textbook, but it is good to know how chloroprene is prepared. So here we take up alkyne, that is ethine, and two molecules of ethine undergo dimerization. This is done in presence of ammonium chloride, which is basically an acid catalyst, and copper chloride at about 343 kelvins. This would result into formation of CH2 double bond C, H, and then C triple bond CH. And this is called vinyl acetylene, right? This is your vinyl part. If you remember it properly, this is your vinyl part. And now this vinyl acetylene is treated with HCl as per Markovnikov. And you will have the triple bond being attacked. C gets Cl. And this is your chloroprene that you get. So this synthesis is a small synthesis. Maybe those of you who are doing only boards may avoid this, but for those who are doing competitive exams, they may at least know this, right? Now we're not taking up Buna S and Buna N here. We've already done them. And now, therefore, my next topic would be molecular masses of polymers.